So, good afternoon, my dear students. My name is Dr. KCH Apparao, working as an associate professor in Mechanical Department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous classes, we discussed the introduction of the heat exchangers, importance of heat exchangers, and applications of heat exchangers also we discussed, and the classifications of heat exchangers also we discussed. Next, we discussed the design of heat exchanger. So, mainly for the two types of the flows. One is the parallel flow, and next one is the for the counter flow. Okay. So, design of heat exchanger, design of uh, parallel type of heat exchanger. That is the LMTD method is there. We already discussed, and for the counter flow also we derived the LMTD method for the design of heat exchanger. Okay, so next LMTD method is only possible if we know the all the temperatures like inlet temperatures of the cold fluid and outlet temperature of the cold fluid. Next to inlet temperature of the hot fluid and outlet temperature of the hot fluid. If we know these four temperatures, then you can prefer the LMTD method. Otherwise, uh, we cannot consider the LMTD method for the design of heat exchanger. So, suppose if we know inlet temperatures only, just like hot fluid inlet and cold fluid inlet, because in some cases it is not possible to measure the outlet temperatures, because those outlet terminals are just connected to another system. We already discussed in previous classes also. In this case, just we have prepared the NTU method also. NTU method for the design of heat exchanger. This one also covered in previous class. NTU method for the parallel flow we already discussed in previous class, and NTU method for the design of counter flow heat exchanger already discussed in the previous classes. Okay, so in this class we will discuss about uh, cross flow heat exchanger. Cross flow heat exchanger. We'll see. So counter flow, just it is possible only in double pipeline, just like it is the inner pipe. Outer envelope is like this one. Uh, so in this case, just like we consider the either parallel flow or counter flow. Okay. So cold fluid inlet, cold fluid outlet. Okay. So hot fluid uh, inlet to hot fluid outlet. So in this type of double pipe heat exchangers, we prefer the LMTD method. So so in this case, just like we will see two types of the flows. One is the parallel flow heat exchanger. If the both hot fluid and cold fluid parallel to each other and the same direction, like this one. Otherwise, you can take like this one. Hot fluid entering, hot fluid leaving, cold fluid entering, and the cold fluid also leaving. Both are in the same direction and parallel to each other. So this is called parallel fluid exchanger. But in case of counter fluid exchanger, just opposite to directions are opposite. Just hot fluid inlet and hot fluid outlet. We already discussed in previous classes. Both are parallel to each other but in opposite direction. So in this type of double pipe heat exchangers, we will prefer the both, just like parallel flow or counter flow heat exchanger. So now we'll see cross flow heat exchangers. What about the cross flow? So other than the double flow heat exchangers, just like cell and tube type heat exchangers, so we prefer the cross flow heat exchanger. We'll see. So if a heat exchanger other than the double pipe type, if it is double pipe type, just we prefer the parallel flow or counter flow. So other than the double pipe heat exchangers, just like we prefer the cross flow heat exchanger. Okay, the heat transfer is calculated by using the correction factor. It is very important. Correction factor, it is simply represented by F applied to the LMTD for the counter flow heat exchanger pipe arrangement. So cross flow heat exchanger very similar to counter flow heat exchanger, but only we will add the correction factor. Okay. So same formula, Q is equal to overall heat transfer coefficient into area into F is the correction factor. We have to add this one, and delta TLM, logarithmic mean. Okay, so this is same formula for a counter flow heat exchanger, delta TM. This is same formula for the parallel flow heat exchanger also, but delta TLM formulas are different. But delta TM formulas are different for the counter flow compared to parallel flow. But here we consider for the cross flow, we consider the counter flow parameters or counter flow temperatures. So just here, just like we'll add only correction factor F. So then the final formula is equal to Q is equal to UA F into delta T LM, logarithmic mean. So values of a correction factor, finding the value of the correction factor. So it is very important. So we can find the correction factor based upon the type of the figure. So we can collect the, or we can measure the correction factor from the data book. Okay, so for this one you have to use the data book. So based upon the type of figure, just like one cell and many tubes and two cells and many tubes. So in that conditions, just like just I want to explain, I want to show some figures, different types of the cell and tube type of figures. So based upon the figure we can find the correction factor. Okay, so here just like here just it is very similar to counter flow heat exchanger. Same formula will be used for this one also. Q is equal to UA F into delta TLM. So delta TLM formula is it is equal to delta TLM formula in the counter flow heat exchanger. Okay, so hot fluid inlet to minus cold fluid outlet minus hot fluid outlet minus cold fluid inlet. You know that one. This is the delta T1. This one is the delta T2 ln delta T1 by delta T2. Same formulas. So you know about delta T1 and delta T2 because we have already discussed about these things. Okay. Now we'll see some types of the figures, just like some types of the cell and tube type arrangements. Okay, so figure 10 10.8. So correction factor plot, these are the plots. This is the correction factor values. So here just like R values and the P values, these are the constants. They here there is some formulas to find the R and P values. Just like R is the capital T1 minus capital T2 by small t2 minus t1. So don't confuse that one. Capital T represents the just like hot fluids, and small letters represents the cold fluid. It means T1 means T hot fluid inlet minus T hot fluid outlet by T cold fluid outlet minus T cold fluid inlet, because these are the familiar terms for in previous classes also we used this one. Just like we can use this type of formula or similar to this type we can use. So similarly P is the formula, just like small letters means so capital T C naught minus T C I divided by so T H I minus T C I. Okay, so you can use this type of formula or this type of formula. Okay, so by using this R and P, so R is the graphs just like curved lines, and the P is the vertical lines. So the intersecting point, just like the intersecting point between the R and P, which shows the vertical line, just like vertical values. So that is the correction factor. Just you have to measure that one by using the data book. So for this one, for solving the cross flow type heat exchangers, first of all, you have to identify or you have to understand the numerical thoroughly and which type of flow is there. It means so what type of arrangement. So heat exchanger arrangement is there. Here one cell pass, it is only one cell pass, and 2, 4 are any multiple tubes. So this figure only represents only shows the one cell pass and many tube passes. One cell, many tube passes. Tube passes means either these 2 or 4 are just like many. Okay, so for this one, just we have to use this type of figure. So next we'll see another figure. So this is 10.9 figure. We'll see. So here correction factor for the 2 cell passes. Here 2 cells are there, and 4 or 8 or many multiple tube passes. These are the multiple tube passes. So this is the one cell, this is the another cell. So 2 cells and many tube passes. For this one, just like if the condition is this like this, just you have to prefer this figure to find the correction factor F by using the constants P and R. You know the formulas for the constants R and P. Okay, so you know that one. R is nothing but inlet temperature minus hot outlet temperature divided by cold fluid outlet temperature minus cold fluid inlet temperature. Okay. Similarly, P is the cold fluid outlet temperature minus cold fluid inlet temperature by hot fluid inlet minus cold fluid inlet. Okay. So these are the formulas. If you know the 4 temperatures, so we can prefer the and we can solve the just like cross flow heat exchanger numericals. Okay, so this is one type of just like heat exchanger. Now we'll see one more type. So here correction factor plot for the single pass cross flow heat exchanger. So here the condition is flow is vertical to each other. This is the hot fluid and just flowing vertically. Cold fluid is flowing horizontally. So these are flowing individual cells. So it means the fluids, hot fluid and cold fluid does not mix with each other. So this condition is the both fluid is unmixed. If the both fluid is unmixed. Okay. So and single pass cross flow heat exchanger. So if the condition is like this one, just you have to choose this type of diagram to solve the correction factor by using the just like ratios. It means constants R and P. Okay. So this is the one type of flow. So we'll see one more. So this is the here. One fluid is mixed, but another fluid is not mixed. It means cold fluid T1 minus small t1 to small t2. Otherwise, TCI, TC0. So this cold fluid is flowing through separate cells like this one, like this. So cold fluid does not mix with each other here, but hot fluid is flowing same cell, just like there is no individual cells, so individual pipes. So the flow is the single cell. So here hot fluid is mixed one, cold fluid does not mix with each other. So this is the condition is single pass cross flow heat exchanger. This is the single pass cross flow heat exchanger, and one fluid is mixed. That is the hot fluid is mixed and cold fluid is not mixed. Okay, so if the condition is like this one, you have to choose this type of figure. So based upon these figures, just we can find out the correction factor. By using the correction factor, we can find out the cross flow heat exchanger numerical. We can solve the cross flow heat exchanger numericals. We'll see. Just here, just we'll solve one numerical uh, based upon the LMTD method. Initially, just I'm taking LMTD method. So because cross flow is completely related to LMTD. Okay. So after that, we will solve the uh, cross flow heat exchangers. So this is the just like water at a rate of 68 kg per minute is heated from 35 to 75 degrees Celsius. So water, this is the cold fluid. You know that TCI is equal to 35 and TC naught is equal to 75 degrees Celsius. So this is heated by an oil having specific heat. The specific heat of the oil also given, that is the 1.9 kilojoule per kg Kelvin. Okay. So the fluids used in a counterflow double pipe heat exchanger. This is the counterflow double pipe heat exchanger. Okay. So not a cross flow. Okay. So same numerical will apply for the cross flow also. First we'll solve this one for the counterflow heat exchanger by using the LMTD method. Then solve the same numerical for the cross flow heat exchanger. Okay. The oil enters hot fluid temperatures are given. THI is equal to 110 degrees Celsius and TH naught hot fluid leaving temperature, that is the 75 degrees Celsius. Okay. So the overall heat transfer coefficient also given, that is the U is equal to 320 watt per meter square Kelvin or degree Celsius. Okay. So here just we have to find the, or we have to calculate the area of the heat exchanger. Area of the heat exchanger. So for this one, just first of all, you have to find the rate of heat transfer. Q. You know the formula for the counterflow. Okay. So this is the data. It means cold fluid inlet is equal to 35 degrees Celsius and cold fluid outlet is equal to 75 degrees Celsius. And hot fluid inlet is equal to 110 degrees Celsius and hot fluid outlet is equal to 75 degrees Celsius. This is the data, and overall heat transfer coefficient also given 320 watt per meter square degree Celsius. Okay. So next specific heat of the oil also given. And mass flow rate of the water also given. Specific heat of the water, we know that is the 4.18 kilojoule per kg Kelvin. You know that value. Otherwise, just 4180 specific heat CP for water, or CC you can take like this one, because water is a uh, cool fluid here. So CC is equal to 4.18 or 4180 kilojoule per kg Kelvin or degree Celsius. Okay. So specific heat of the this one also, specific heat of the oil also given, but mass flow rate is not given for this one. Here water mass flow rate is given, and also you know that the specific heat of the water. So two parameters, you know that, you know the formulas according to thermodynamics. Q is equal to MC into CC into T hot fluid minus cold fluid outlet minus 2 cold fluid inlet. So temperature difference of the cold fluid is equal to similarly MH and CH hot fluid inlet minus hot fluid outlet. So temperature difference of the hot fluids. So, you know this formula, so we already discussed in previous classes also. So here just like MC is given, that is the 68 kg per minute converted to seconds. So kg per minute you have to convert it to kg per second. So it means 68 by 60 kg per second. Okay. And CC also you know that value. So CC specific heat of the water, that is the 4.18 kilojoule per kg Kelvin or 4180 joule per kg Kelvin or degree Celsius. Okay. So you know that parameters MC and CC and TC naught and TCA. Then you can take this formula to find the rate of heat transfer in the uh, cool fluid. Okay. Just Q is equal to MCCC into TC naught minus TCA. Just here you have taken this one. Okay, so MC is the mass flow rate, that is the 68 kg per minutes given, but converted to kg per second. Next to CC is the 4.180 kilojoules converted to joules, and TC naught is equal to 75 degrees Celsius, and 75 TCI inlet temperature of the cold fluid is equal to 35. If you solve this one, we'll get this one. So 189.5 kilowatts, it is the rate of heat transfer in that counter fluid exchanger. Okay. So by using this data, you have to find out the area of heat exchanger. Okay. So already solved this one. So you know that Q is equal to UA into delta T LM. So first of all, you have to find out the delta TLM. You know that delta TLM formula is equal to same formula, delta T1 minus delta T2 by Ln delta T1 by delta T2. You know this formula. Okay. So delta T1, you know that if you just graph, you know the graph. So cold fluid inlet to hot fluid inlet to hot fluid outlet. Okay. So in counter flow, opposite direction. So flow is in opposite direction to each other. So here cold fluid inlet to and hot fluid outlet, cold fluid outlet. Okay. So this is the delta T1. You know that this is the delta T2. Know that delta T1 is equal to THI THI minus TC naught. Okay. Delta T2 is equal to TH naught minus TCA. Okay. So opposite to inlets. So inlet and outlets. So you know that delta T1 is equal to this one, delta T2 is equal to this one. You know that delta T1 means THA minus TC naught. THA is equal to 110 minus TC naught is equal to 75. So we can calculate that one. Delta T2 is equal to similarly TH naught is equal to 75, TCA is equal to 35. Just like this is 40, this one is the 35. So you know that delta T1 and delta T2, if you substitute the values of delta T1 and delta T2 in this formula, we will get the delta TLM. Okay. So here already I have prepared the PPT for this one. Just you can check this one. Okay. So this is the okay. So just delta TLM is equal to you know this formula, hot fluid inlet minus cold fluid outlet. So this is the delta T1. So this is the delta T2. You know the formulas. Okay. Ln delta T1 by delta T2. Substitute the values. Hot fluid inlet is equal to 110 degrees Celsius. Hot cold fluid outlet is equal to 75, and hot fluid outlet is equal to 75. Cold fluid inlet is equal to 35. Okay. If you substitute these values, and you will get the value of delta TLM, logarithmic mean value. This is the 37.44 degrees Celsius. Okay. Then you know the formula, just like Q is equal to UA into delta T LM. Okay. Just you have to find the value of area. Then area is equal to Q by U, overall heat transfer coefficient, into delta TLM. Substitute the values. You know the value of Q and you know the value of U. because it was given, and the value of delta TL. So because we already solved that one. So then the area is equal to like this one. The area is equal to, so Q by U into just like delta TL. Okay. So this is the area. So this is the just that simple method, LMTT method for the counter flow. Okay. So here just like same numerical is considered for the cross flow. Okay. So instead of double five heat exchanger of the example one, so what was solved in this previous slide. So it is decided to use the cell and tube heat exchanger. Cell and tube heat exchanger. It means one cell, so maybe many tubes. Okay. So that is the with water making one cell pass. So through cell water is passing, and oil is passing through two tubes. So it means one cell and two tubes. It means so first figure you have to choose that one, already explained in previous slides. Okay. Here also calculate the area required for this heat exchanger. Okay. Assuming the overall heat transfer coefficient, that is the 320, same value here and there also. Okay. So just like here, the design has been changed. So instead of double puff heat exchanger, cell and tube type heat exchanger has been taken. Okay. So here one cell and two tubes. Okay. So based upon this condition, you have to choose the diagram, so which are given in the data book. So by using the data books, we can collect the and we can find the correction factor and we can solve the numericals here. Okay. So we'll see how to solve this one. To solve this one, just like we determine the correction factor first of all. Okay. For the correction factor, you have to choose the diagram, which diagram is related to this numerical. Okay. So you know that that is a one cell and two tubes. Okay. So one cell and two tubes. So that is the first figure. That is the figure 10.8. Okay. So we can check that one. So you have to choose this one using the LMTD method, same method, and we can solve the uh, cross flow heat exchanger numerical. So same cross flow heat exchanger very similar to counter flow heat exchanger, because delta T1 values and the delta T2 values equal to counter flow heat exchanger. And it means in cross flow heat exchanger and counter flow heat exchanger, both are same for the delta T1 and T2 values. It means same graph we'll see in cross flow heat exchanger also. It means hot fluid inlet and a hot fluid outlet, cold fluid inlet and cold fluid outlet. Okay. So this is the delta T1, this is the delta T2. Same diagram, same system will be applicable for the cross flow heat exchanger also. Okay. So it means cross flow heat exchanger and counter flow heat exchanger both are very similar, but only correction factor will use in cross flow heat exchanger. So how to find the correction factor is very important. Okay. So for this one, we have to understand the numerical condition. So how many cells are there, how many tubes are there. So based upon this data, that data, just you have to prefer the figure which is related to that numerical. Okay. So here we will see. So remaining parameters same, because the same numerical is solving here also. You know that inlet temperature of the hot fluid is equal to 110 degrees Celsius, and the outlet temperature of the hot fluid is equal to 75 degrees Celsius, and the cold fluid outlet is equal to 75, cold fluid inlet is equal to 35. So same parameters, and U also same, that is 320. Okay. So watt per meter square Kelvin. Okay. So first of all, we will find the correction factor, F value. F is depend upon the R and P. You know the formulas. R is equal to THA minus TH naught by TC naught minus TCA. So you know the formulas here already is given. You can check this one. you can represent these formulas either like this one or capital letters and small letters. Capital letters shows the hot fluid and small letters shows the cold fluid. One shows the inlet, two shows the outlet. Okay, so don't confuse that one. So this is the formula for the P, this is the formula for the R. Okay, so P is equal to Tc naught minus Tca. Tc naught is equal to 75 minus Tca is equal to 35 divided by hot fluid inlet 110 minus cold fluid inlet 35. Okay, so by using this one you have to find out the P value. Okay, so this is the formula for the R. R is equal to hot fluid inlet minus hot fluid outlet. So it means 110 minus 75 divided by cold fluid outlet minus cold fluid inlet 75 minus 35. Okay, so we'll get the value of R and P. By using the R and P, we can find out the F by using the figure. Okay, you know the same formula. So here we will see the F factor, except this one. So this is the formula is very equal to counter fluid exchanger. You know that. So Q is equal to UAF into delta TLM. You know the formula for the delta TLM, that is delta T1 minus delta T2. Delta T1 is equal to hot fluid minus cold fluid, hot fluid inlet minus cold fluid outlet. So delta T2 is equal to hot fluid outlet minus cold fluid inlet. So same formulas. Okay. Now we'll find the F value, correction factor F. Okay, so here, so you know the formula P and the formula of R. If you substitute the values of inlet and outlet parameters and values of the hot fluid and cold fluid, then we'll get the value of P and value of R also. Okay, so value of P is equal to 0.534 and the value of R is equal to 0.875. So you know that this is the one cell and two tubes. Okay, so one cell, it is very important. Two tubes or four tubes or multiple tubes, we can use that one. That is the figure 1, that is the 10.8. We can refer that one. So 5 P is equal to 0.5, R is equal to 0.8. So you know that that is the figure is the so this is the first figure, one cell and two tubes. Okay, you can use this one. P is equal to 0.5, P is equal to 0.5. So this is the P value. So this one is the 0.5. Just R is equal to 0.8. So this is the 0.8 curve. Okay, so if you 0.5 and 0.8, so this is the touching point, 0.85 something. Okay, we'll check that one. So correction factor is equal to F is equal to 0.81. If you see that one correctly. Okay, so 0.82 T3 3. So okay, no problem. So it will be it will not so affect the answer. Okay. So 0.8 more than 0.8, so you have to take the F value. So in this way, just like we have to find out the F value by using these diagrams which are placed in the data book. So by using data book, you can solve the cross flow heat exchanger numericals only. Okay, just you have to remember this one. So for this one, you have to remember the formula P and R. So those formulas are also given in the data book also. Just you have to identify. So some data books, small t1, capital T1, capital T's are represented by hot fluid inlet and hot fluid cold fluid inlets. Just don't confuse that one. Okay, so if you know the F value, then you can find out the delta TLM value. Delta TLM already we solved in the numerical one, that is the value is equal to 37.441. Okay, so and U also given 320. Then you can substitute all the values and you can find out the area. So okay, so you know that you know, Q is equal to UAF into delta T LM. Okay. Then area is equal to Q by U into F into delta T LM. So Q already we find that one. Just we solved that one. 189.5 kilowatts. So into 10 to the power of 10 cube divided by overall heat transfer 320. Okay. So into F is equal to 0.81. Okay. 0.81, 0.83, no problem. And delta TLM. So that is the 37.44. Okay. So then we'll get the area. So the area is equal to 19.53. So 19.53 area for the cross flow heat exchanger. Okay. So previous we got the area for the counter flow heat exchangers. Okay. So in this way, just like we can solve the different numericals which are related to cross flow heat exchangers by using the correction factor. So finding of correction factor is very important. For this one, you have to use the data book. Okay, we'll see one more numerical, then we'll conclude this class. Okay, a heat exchanger like that shown in the figure. Figure is given just like figure that here. I didn't give the figure. So figure shows the how many cells and how many tubes are there. Okay, so figure is used to heat an oil in the tubes. Heat an oil in the tubes. So from 15 degrees Celsius to 85 degrees Celsius. Okay. So steam is the hot fluid here. Oil is the cool fluid. Cold fluid is the oil and hot fluid is the steam. Okay. So cold fluid parameters are given. So cold fluid inlet TCI is equal to 15 degrees Celsius and TC0 is equal to 85 degrees Celsius. Steam parameters. So steam enters, it means THI is equal to 130 degrees Celsius and TH0 is equal to 110 degrees Celsius. So four parameters, four temperatures are given, then you can choose the LMTD method. You know that one. So with a mass flow rate of the steam has been given. Mass flow rate of the steam, we can say MS or MH is equal to 5.2 kg per second. So it was given in second also. The overall heat transfer coefficient also given, that is a U. U is equal to 275 watt per meter square degree Celsius or Kelvin, anything. Okay. So and the specific heat of the steam also given. Specific heat of the steam CH or CS. CS shows the steam or CH shows the hot fluid. Here hot fluid is equal to steam. So don't confuse this one. Otherwise, you just write this one. So this is the MH and this is the CH. So CH value is equal to 1.86 kilojoule per kg Kelvin. 10 cube into joule per kg Kelvin. Okay, degree Celsius. So here also you have to find out the surface area. Surface area. Okay. So just like here we can find the all parameters which are related to hot fluid. Hot fluid of the mass flow rate of the hot fluid is given. Specific heat of the hot fluid is given, and inlet and outlet temperature of the hot fluid is given. Then you can find out the Q value. So you know the formulas for the Q, MH and CH into THA minus TH0 is equal to, it means hot fluid temperature differences is equal to MC and CC TC0 minus TCA. So according to thermodynamics formulas, laws, you know this formula already. Okay. So here just like I'm taking the MH, so hot fluid related formula, because all the data which are related to hot fluid are given here. So Q is equal to MH and CH into delta TS, means hot fluid inlet minus hot fluid outlet. So these parameters are given. Then you can solve the Q value. It means mass flow rate is equal to 5.2 kg per second into, so 1.86 kilojoule per kg Kelvin, just like into 10 cube. I have to write this one into, so hot fluid inlet is the 130, hot fluid outlet is equal to 110. Okay, so if you solve this one, you will get this one 193 kilowatts. Okay, so 193 into 10 cube watts. So this is the value of Q, value of Q. So now we have to solve the correction factor F. It is very important. Okay, here what is the condition here? We'll see in figure. So figure is not given. Sorry. So according to this one, just like figure 10.11. Okay, so 10.11 means, so we'll see that one. Figure 10.11. This is the, it means, so one fluid is mixed, another fluid is not mixed. So this is the condition. Okay, this type of figure has been given in that numerical. Okay, so one fluid is mixed, another fluid is not mixed. So by finding P and the R values, by using these two parameters, you can find out the F value. So F is nearly 0.9 something. Here you can see, okay, 0.97. Okay, so we can find the F value by using the P and R. Okay, I already explained that the process how to find the F value by using the P and R, by using the data book. Okay, so then delta TLM, you have to find out that one. So it is very this formula is equal to counter flow heat exchanger, delta T1 minus delta T2, delta T1 by delta T2. Okay, delta T1 for the counter flow, hot fluid inlet to cold fluid outlet. Okay, so opposite directions, delta T2 is equal to hot fluid outlet to cold fluid inlet. Okay, so you know the values, hot fluid inlet value, inlet is equal to 130, or the cold fluid inlet is equal to 85. Okay, hot fluid outlet is equal to 110, cold fluid inlet is equal to 15. Okay, if you substitute these values, we will get the delta TLM. Okay, if you know the delta TLM and correction factor F, and you know the value of U also that was given, and Q also already find that, then you can find that value of area. Okay, you know the formula. So that is the Q is equal to UA into F into delta TLM. Okay, here you have to find out the area. Area is equal to Q by overall heat transfer coefficient into F into delta TLM. Delta TLM. You know all the values. Okay, Q value is equal to 193 into 10 cube divided by, so that is the overall heat transfer coefficient is equal to 275 into F 0.97 into delta TLM is equal to 66.9. Okay, if you solve this one, area, you get this one 10.82, sorry, 10.82 meters square. Okay. So in this way, just like we can solve the cross flow related numericals by using the data which are given in the data book. So for this one, just you have to understand the numerical, what type of setup, what type of flow arrangement is there, and cell in between the cell and tube, how many cells are there, how many tubes are there. Okay, so based upon this, that condition, just you have to prefer the figures which are just like available in the data book. Okay, so by using those figures, then you can find out the correction factor. You know that correction, for the correction factor, P and R values are constants are very important. You know that formula for the P and R. So by using those formulas, we can find out the P and R. By using those P and R, we can find out the correction factor with the help of the data book. Okay, if you know the f values remaining same process for the counterflow, so similar to counterflow, then you can solve the whatever the parameters will be asked in the numerical. Okay, thank you for this listening class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.